Giant Leap with Taylor Wilson.
Welcome to Giant Leap. Today we're talking about methane. Joey, what do you know about methane?
I mean, I guess there's the obvious.
You could say it.
You know, we've all
You can say it.
there's the obvious fart joke here.
Yeah.
So I guess
Methanogens in our gut pumping out large amounts of methane.
that's exactly what I was gonna say.
Yeah.
The same words.
Yeah.
But you know, it smells bad.
No, it actually doesn't. That's a common misconception.
Oh.
You know, the smell of natural gas, which is primarily methane, is actually added as odorant to make sure you know it's there if it's leaking. The smell of
I'm
the
adding
human
a smell to methane.
The smell of the human gut is similar. You know, think about these like mercaptans, these sulfur-containing compounds. It's not
just
the methane
other
itself. Methane itself is odorless.
So sulfur-ish is
Sulfur compounds.
okay. So yeah, methane. It's a compound of elements. I don't actually even know what it's made of.
Yeah. So methane is CH4. So you can think of this central carbon molecule bonded to 4 hydrogen atoms. That is
Carbon and hydrogen.
Yeah, which makes it a great fuel. That's why it is the majority of natural gas. It is this gas that is highly flammable because you can easily take that carbon with those 4 hydrogens and combust it into CO2 and water vapor.
Got it. Yeah, and I think I did know that methane was very flammable.
Yeah.
So,
Yeah.
okay, that's pretty much all I know about methane.
Okay.
Why are we talking about it today?
Because methane is a really interesting gas, and it's a very important gas for a variety of things, not least of which our environment and our climate.
Okay, I guess I did know that it's like a greenhouse gas.
It's a greenhouse gas.
Because I know this because like cows contribute a lot to
Exactly.
like dairy farms and beef production contribute a lot to climate change, right?
Yeah, absolutely.
Yeah.
And so it's an important kind of gas to think about. It's not the canonical greenhouse gas that everyone thinks of, this carbon dioxide.
CO2 from
but
cars.
But it's actually quite a bit more powerful. Over the course of 20 years, it's maybe 85, 90 times as powerful a greenhouse gas as CO2. And even over a longer time scale, like 100 years, it's 25, 30 times as powerful as CO2 as a greenhouse gas.
So that a cow is worse for the environment than like my car.
Maybe not exactly. But the molecule itself, you take a molecule of CO2 and a molecule of methane, that molecule of methane is much more effective at trapping heat, of trapping infrared radiation than the carbon dioxide. But it doesn't last in the atmosphere as long as CO2. So if you turn off the methane or turn down the methane, that's a really good way to kind of impact the anthropogenic or human-caused climate change that is happening right now.
So you say it doesn't it's a much shorter lifespan. So like CO2 is up there for what, like 100 years and methane's there
Yeah, we
10?
typically talk of half-lives. So CO2 might have a half-life around 100 years, methane maybe 10 years as its half-life.
Oh wow, so much. I was pretty close.
And it really has to do with what happens to methane when it goes in the atmosphere. So in the upper atmosphere, we're talking troposphere and the kind of upper regions of the atmosphere where these gases end up, there are radicals. And radicals are these very reactive molecules that have formed primarily from photodissociation. So think light from the sun breaks down molecules in the upper atmosphere, create these reactive radicals. They actually break down methane, and they break down methane into, in some cases, CO2, water, other gases. And unlike CO2, which primarily has this sink where it dissolves and forms rocks and things like this, the methane can be actively broken down in the upper atmosphere pretty effectively. But while it's there in that kind of residency time while the methane is hanging out, it is an incredibly strong trap for heat. And so as we look across the kind of spectrum of anthropogenic, human activities that are contributing to our changing climate, the sources of methane could actually be really important in trying to combat this challenge. So you mentioned cows, so agriculture is a big part of it. This is what we call biogenic methane, and biogenic methane is just methane that originates from animals or
I'm assuming
biological life.
Methane is originating from humans
to
some degree.
It can. Most of this methane originates from these organisms called methanogens. And methanogens are just basically microbes that eat food, and the byproduct of that is methane.
Okay. Are these in the ocean?
They're everywhere. They're in swamps. They're in our gut. They're in ruminant guts. They're in cow the cow intestinal system.
Okay.
And
they're just one of the things that helps us digest.
yeah, they're an important, if you think of cows, for example, they're an important way to take things like cellulose and break it down into something useful, sugars that can be used for metabolism.
Taking hay, turning it into
But
energy.
again, the byproduct of that is this gas that floats up and traps atmospheric heat. And there are lots of natural sources of that. Swamps and things like this are big sources of biogenic methane. But
I know there's methane like trapped under the ice caps.
that's another form of methane that we have to worry about. But if you think about from human activities, there are quite a few things we do in our everyday lives that are contributing to this problem that, before humans were around, weren't pumping out massive amounts of methane. And so examples of that could be agriculture. Maybe it's, farming rice or something that releases large amounts of methane. Maybe it is.
Wait, why would rice release methane from the soil?
So the way that we do that farming, flooding and causing the methanogens to, convert some of those substrates into methane, or, cows and agriculture involving, these large ruminant animals. This is a portion of the human impact on the kind of global changing climate. It's maybe not the largest portion, but it's a portion that
It's significant enough.
There might be small things that we can do that farmers can do that make small changes that actually really end up, affecting how much methane we're releasing. So maybe that's so-called low-hanging fruit that we could do, as opposed to, massively transitioning, the way we live our lives in the form of, power generation or vehicles or something like that. But, it could have a big impact. So those are what we call biogenic methane sources, the cows, the swamps, things like that. The other sources are what we call abiotic or fossil methane. And that's really canonically natural gas. So
this is just like stuff like rocks have broken down. There's methane in that deep in the crust.
Yeah, or it's really old life. So there's a reason we call fossil fuels. So it is the fossilized, quote unquote, remnants of ancient life that over millennia and the temperature and the pressure has been crushed and transformed into these shorter hydrocarbons like methane, and trapped by typically an impermeable layer of like salt or clay, for example.
So like if I die and then you put me in the ground, and then like
bury you with a bunch of clay and sediments.
Yeah, like a million years later, like some of my body turns into methane. And then like, you do that a bajillion times with all those microbes from, millions and millions of years ago and the dinosaurs and everything. And you
primarily ocean sediments. But yeah, you think of all that stuff getting buried under rock and clay and sediment, and you have a great trapped reservoir of these gases. And those gases, especially in the 20th century, were an amazing boon. They allowed us to electrify, think street lamps and all of these things, and, create stoves, and it was a relatively clean burning fossil fuel as opposed to coal or oil or even like biomass that
How do we pull this out of the ground compared to oil?
Similar drilling techniques. You drill a hole in one of these cap formations that has a say like a clay layer cap. You perforate the formation, and then the pressure of the formation forces out the gas or
then we
the
capture
oil.
it in some sort of tank.
Yeah, or force it into a pipeline and distribute it. That's the natural gas infrastructure, which is fairly similar to oil production.
Okay. And natural gas is not like a green energy.
The combustion of natural gas generates CO2. It's cleaner than other fossil fuels, but it still releases some harmful air emissions and of course carbon dioxide. So anyway, we have this problem of abiotic methane, which is typically natural gas. That also seems to be a relatively surmountable problem that could be kind of a quick fix or a quick recipe for abating some of the climate change that we're seeing. And there's actually a financial incentive to do it. If you think about it, right, like there are massive amounts of infrastructure in this country for the production of oil and natural gas. Lots of wells, lots of pipelines, lots of distribution hubs. And a lot of them leak methane. They leak natural gas.
Oh, okay.
And so in that case,
and we can smell that because we're adding an additive to it.
Only if it has had an odorant added to it. Now that's usually downstream. That's in the distribution part of the infrastructure.
We're not doing that right at the beginning.
Not right at the beginning. But if you think about it, all of this infrastructure, all these wells and everything, if they're leaking natural gas, well, that's natural gas that is causing a very strong impact on the climate, very, very strong greenhouse warming potential.
Yeah.
But it's also economic revenue that's being lost. The company that's producing the natural gas, if they're losing it, they're not generating revenue from it.
And like it's like worse for the environment, and we're not like
Exactly.
It's like doubly bad.
Exactly.
Okay.
So I think there's really low-hanging fruit there in incentivizing companies to try to mitigate the leaks in their infrastructure. Some of these leaks are accidental. I mean, we saw devastating effects of this. There was one down in Southern California not too long ago that blew out. This gas well blew out and vented natural gas in the atmosphere for a very long time.
If it ignites, it's like blowing up all the gas down the pipe, or
no, because it has a explosive range or flammable range. If it's over a certain concentration, it's not flammable. If it's less than a certain concentration, it's not flammable. So in the pipe, it's not going to explode. But if it gets out in the air and if it mixes in that right, what we call stoichiometric ratio of air and fuel, it can ignite and cause catastrophic explosions. We've seen this with natural gas transmission. But anyway, long story short, there are accidental releases, catastrophic accidental releases of natural gas. But really, most of the release from anthropogenic, sources of that abiotic natural gas are just, I don't know if laziness is the right word, but it's just, a leak here or a leak there.
It just happens, right?
Crack or a bad weld or, whatever. And so if we could incentivize, oil and gas companies to, take that revenue, take the revenue from that gas instead of, putting it in the atmosphere, that could be a very good thing. Historically, it's just been very hard to see where that natural gas is coming from. And so one of the things I've been involved in is trying to come up with better ways to ascertain the so-called methane budget, or where the atmospheric methane is coming from. And we've developed a large number of technologies to do this. Ground sensors that actually use lasers bouncing in between two mirrors, where even though the device itself might be, literally 10 or 20 centimeters in length, it could have mean free path lengths of kilometers by the time that laser beam bounces back and forth inside.
I don't know. Oh, hang on. You totally lost.
Okay. So imagine you take a tube with two mirrors and you inject a laser beam.
Yeah, it's bouncing back and forth.
Yeah. If you didn't have the mirrors, the laser beam would just go that distance, and your detection sensitivity would be based on how much those gases absorb the laser light in that distance.
So you lose a little bit of light.
Usually, a little bit of absorption of the laser beam because of the methane. Again, we talked about it absorbing infrared energy.
Or different gases absorb different amounts of.
Exactly.
Okay.
But if you put two mirrors in that tube and you bounce the laser light between those two mirrors thousands or in some cases, many more than that, millions or billions of times, that laser light is going back and forth. The path that laser light takes through the gas is much longer, and that improves the sensitivity. And so we can take these, what we call cavity ring down spectrometers, out into the field and very accurately measure the concentration of methane and also the isotopic composition. How much of it is biogenic methane that's coming from life, and how much of it is the abiotic methane that's coming from like a natural gas well.
Okay.
There's other cool things you can do. You can use FLIR cameras. If you take a camera that's looking in the infrared spectrum, you can see the absorption of a plume of natural gas or methane because of that absorption of the infrared light.
Right.
So FLIR cameras are an interesting way. Like you can take
FLIR infrared camera, you can see it. Basically, it shows you heat.
It shows you heat or the absence of heat,
Yeah.
and you can take it and look at natural gas infrastructure, or honestly, any source of methane. And if the concentration is high enough, you'll actually see the absorption of the heat in the camera image. And then there's even cooler ways, and these are really emerging technologies. There's one new satellite called Methane Sat that is actually doing remote sensing from orbit. So again, using these different parts of the electromagnetic spectrum, observe Earth from space, and with very, very high sensitivity and a very high coverage area, be able to look, is that well emitting methane, or how much methane is coming out of that piece of infrastructure, or that landfill, or that, you name it. So methane is a very interesting gas, and you can even detect it from space. So you can imagine, we're kind of limited in how many times we can go out to a landfill or a natural gas field and haul around one of these FLIR cameras or cavity ring down spectrometers. But if you're looking at Earth from space, your coverage area is so large. You could look, in a given day at literally hundreds of natural gas wells and be able to call up those operators and say, hey, like, you have a problem out here. You should go check that out because, not only are you harming the environment, but you're losing money. So that is the methane problem. It is a strong greenhouse gas. It is something that we want to mitigate, how much methane is going into the atmosphere from human sources. But there are these tools that we have that can kind of mitigate our release of this gas and mitigate our impact in the environment.
How big of a problem is like methane in the atmosphere compared to CO2? Like you said, it's a much shorter lifespan, but it's a much stronger greenhouse gas.
Yeah, I would say on balance, it's maybe less than a quarter, less than a fifth of the total warming that we see is from methane.
And a quarter or a fifth is not insignificant.
So it is something that we should try to find areas that we can kind of cut back on our emissions, come up with better ways to design landfills, because again, that methane coming out of a landfill is useful
stuff, and it's just like that's just trash breaking down.
Exactly, your hamburger that you tossed in the trash and then it gets buried in a landfill. Yeah, it's breaking down into methane. And one thing that you can do is as you're building the landfill, as you're lining and capping the landfill, you can trap that natural gas, that methane, and generate electricity from it.
Yeah, we talk about carbon capture. That's like a whole thing in trying to slow global warming. But is methane capture also?
Certainly, and specifically in landfills, that is a really useful way to help mitigate the problem and generate some benefit from the gas.
Once it's in the atmosphere, is there anything we can do to capture it then, or is that
it doesn't
more
stick around as long as CO2, so there aren't really these like carbon sequestration type projects, carbon capture projects, like there is for carbon dioxide. But again, the best thing we could do is just not emit it in the first place. And if we do that, because it has a shorter residency time in the atmosphere, we get a faster payback. Our bang for the buck kicks in sooner. And it's important because methane, along with being something that is released from these human activities like drilling natural gas wells and landfills and, large, farms of cows, there are sources of methane that honestly pretty much scare me.
Okay.
These are things like methane clathrates or methane hydrates that are under the ocean, which are essentially...
Are those the ones on the ice caps?
Yeah, they're typically under the ocean where the temperature is very low, the pressure is very high, and you form these compounds where it's essentially methane with some water molecules. And there are, we think, very, very large amounts of these methane clathrates under the water. In fact, so much that there have been proposals to mine that as a source of natural gas. But what becomes really scary is if those get destabilized. And this is why
that means like woken up or shaken, and
as the climate changes or geological forces change, if we get large amounts of that methane that is trapped in these clathrates released, that's where we start to talk about these so-called positive feedback loops with climate change. And there's a lot of debate among climate scientists about the importance of these positive feedback loops. But we know that there are these unstable deposits of methane, and it's a mixture. Some of that is abiotic, some of that's biotic, but the idea is just basically under the water, these cold temperatures and high pressures, they form these deposits. There are other sources, though, of methane that are concerning. Think about all of the permafrost at our poles, where there is large amounts of organic matter that has these methanogens in them. Or maybe not even under the ice, but in frozen, in frozen soil, that as the climate warms, as the climate changes, if that starts to thaw and those methanogens start to really work on it, again, that's a positive feedback loop. So you can imagine the methane going in the atmosphere, trapping more heat, the atmosphere heating up, causing more methane to be released from the permafrost. We don't know how strong an effect that is, but I'm not a gambling person, and I'm certainly not a gambling person when it comes to these kind of things. I think anything we could do to try to mitigate running the experiment on a global scale, probably the better off we'll be. So that's methane here on Earth. It's a fascinating gas. It's a gas that is concerning, but it's a gas that it is endlessly fascinating.
You said methane here on Earth, so I'm assuming now we're headed off into the cosmos.
Yes, which is one place I love to be.
Yes, other than the underground.
And that goes to the other methane problem, and that is the problem of finding transient methane on Mars.
Why do we care?
Because on Earth, most all the methane that we have comes from life. Even the abiotic methane at some point was life that was, used the power of the sun to form these carbohydrates. That got buried turned into natural gas. These are the kind of processes, methanogens, fossil fuels, that we know of producing methane here on Earth. So on a planet like Mars, which we think doesn't have those kind of processes going on, we also don't think has a lot of the geological processes that release abiotic methane, think volcanic activity and things like that. We see, I mean, it may be a fraction of a part per billion, but we see, depending on the time of the year, transient amounts of methane coming into the Martian methane, Martian atmosphere.
Proof of life.
Methane on Mars could be one of our most promising signals of astrobiology. But I do want to put that disclaimer there that there are abiotic sources of methane.
Sure.
For example, serpentinization, which is a transformation of mantle rock with water, can release methane. So, it's not definitive signals of life, but it is promising. And it's one thing I'm really excited that we'll hopefully in the next decade get to go really investigate is where is that methane coming from on Mars, and elsewhere in the universe as we look out and are able to do these spectroscopic searches of atmospheres way far away from Earth. Methane is one of those really prime candidates for
one of the many
indicating that there might be life.
Yeah, cool. All right, well, Taylor, you should be proud of me for the number of times I held my tongue in this episode.
All right, sounds good.
The number of fart jokes that we skipped over.
I'm sure you had lots of them.
I was ready to go, but I held my tongue to let you talk about the actually important and interesting things about methane.
The science of methane. All right.
Yeah, cool. Well, the methane problem it's there. It's interesting. It's something that we're working on, and hopefully, we can do another episode in a year or so talking about how there's some science advancing that is changing that.
Yeah, absolutely.
Cool.
All right. Thank you for joining us this week on Giant Leap.
Yeah. We've got a Patreon if you want to support the show. You can find us, Giant Leap Podcast, on Patreon. We are in audio form wherever you get podcasts, in video form on YouTube. And you can email us at giantleappodcast@gmail.com.
All right. Thank you, guys.
That's one small step for man, one giant leap for mankind.